Alright, let's talk about absolute configuration. Absolute configuration is a method that we can provide the configuration to the structure that is drawn the way it is drawn. By the way, it has got no correlation, absolutely no relation to the alpha that you would get experimentally. But just know that you would be able to predict, just like you can do like E and Z for the structure the way it's drawn, you can do that for optical isomers or enantiomers. So if one of the enantiomer is R, then its mirror image has to be S. So in a racemic mixture, both the R form as well as the S form will persist. Again, it has absolutely no correlation to your D and L from the optical rotation that we discussed earlier, but rather it's something to do with the way the structure is drawn. So it's a theoretical concept. All right, so let's say I have a structure. Maybe I have a OH over here, H at the back. Let's put methyl on top and ethyl on the side. Now, if I were to draw its mirror image, it will look like OH on the left side, hydrogen still at the back, ethyl on the other side, methyl on top. You have to first take the time to assign priority order, and the rules are exactly the same as you learned in the E and Z concept in alkenes. That means higher the atomic number, greater is going to be your priority, and so you would give highest priority to oxygen. In this case, you have to go atom by atom. You have to go to give highest priority to oxygen. So oxygen is going to go with 1. Hydrogen obviously is going to get the last priority. Between the two carbons, since this is connected to hydrogen, hydrogen, and carbon, this is going to be your winner. So second priority. And this is going to be your third priority because it's connected to 3 hydrogens. Now, the second rule is keeping the hydrogen away from you. And in this case, it does happen to be away from us because it's on the dashed line. We have to see how do we go from position 1 to priority 2 to priority 3. Looks like I'm turning in a clockwise direction, and if it is going in a clockwise direction, I'm going to assign it a configuration R. That means I'm expecting its mirror image to be S. Let's see if it is actually S or not. Again, the priority order is OH for 1, ethyl for 2, methyl gets 3, and hydrogen, of course, gets 4. We are going anti-clockwise, and that becomes S. R stands for rectus for right. S stands for sinister for left. All right, let's try a couple examples more. Suppose the question is that you have to provide the R and the S configuration. So provide the R and S configuration for all chiral centers. So you first have to locate where the chiral centers are, or which ones are the chiral centers, and then assign them whether they are R and S. So how would we do that? Notice out of the 5 carbons, only 3 of them are marked chiral, and the reason for that is because this case has a CH2, so there are 2 hydrogens. Over here I have a C double bond, so that's an sp2 hybridized carbon atom, and that is not counted as chiral. So the ones that I have shown, those are my chiral centers. Now, if I was to assign priority, I would say oxygen is highest in priority, followed by this bond, because you're comparing carbon to carbon, but in this case it's connected to 2 oxygens. In this case it's connected to only 1 oxygen, and of course the hydrogen in this case is pointing away from me, so the 4th priority group, which is the hydrogen, is pointing away from me. So in going from 1 to 2 to 3 sounds like I'm going in a clockwise direction, and since I'm going in the clockwise direction, this particular carbon should be R. Now, if you look at the second one, the fact that OH is actually pointing backwards, that basically means that your hydrogen is going to be pointing upwards towards me. So, the trick over here is whenever you have the least priority group which is pointing upwards towards you, whatever configuration you get, invert it, because realize that you are supposed to view the molecule keeping the least priority group away from you. So in order to keep this away from you, don't you think you will have to kind of sit under the molecule? So either view in that direction or view it the way it is and then simply invert it. One of the two ways. So in this case, again, priority order is 1 for the OH. If you look between the two carbons, again, it will be the higher priority to the side that has the aldehyde. The side that has the alcohol will get the third priority. So sounds like I'm going anti-clockwise, so sounds like it will be S, but since hydrogen is pointing towards me, I'm supposed to invert it, and that will become an R configuration. If you notice the last one, again, oxygen is going to get the highest priority, hydrogen is going to have the least priority. This big bulky group, which has the CHOHs, more number of carbons, so that's going to give you the second priority. This side is going to have a third priority. So you're going clockwise, that too is an R configuration. So realize each chiral center in any molecule can be given a specific configuration, and it's pertinent, it's important, because if I were to draw the mirror image of this, then I must draw the R as an S. So this is an R system. And when I draw the mirror image, it must pan out to be an S, S, and S for all the three chiral centers. So keep that in mind. But again, when you're assigning, all you got to do is look at the priority order following the Kahn-Ingold pre-log model, and keeping the least priority group away from you. You have to you have to view the molecule. So this is not something, again, which you will just somehow inherit from me. This is something that you will need to practice and visualize. So different things have worked differently for different people, but again, your aim is to view it from a direction such that the least priority group is away from you. What I like to visualize personally is I like to visualize the chiral center as if it's my steering wheel. And so my priority 1 was right over here, for instance, for this carbon. Priority 2 was right over here. Priority 3 was right over here, and 4 is the spoke essentially. So now in going from 1 to 2 to 3, I'm going clockwise. And if I have to go anti-clockwise, I would invert in the left-hand direction. So you can visualize it as a steering wheel that works. Alternatively, if you have the structure drawn in a manner such that the least priority group is pointing towards you, then you can simply take a look at, again, the spoke pointing towards you in this case, but then you will have to invert the molecule. And so that's another guideline that you can go by. And like I said previously, the R or the S has got nothing to do with the alpha being positive or negative. It is totally possible that you can have an R configuration in which you are carrying out a clockwise rotation of the steering wheel, and that happens to have an alpha which is a negative value. And so that would automatically mean that the S configuration, which is going to have an anti-clockwise steering wheel, and the alpha in that case is going to be positive. So absolutely there is no correlation between dextro and levo and RNS. Those are just completely two different things. Again, recall that. Another way that you can perhaps visualize, and I'm going to take a look at both the Fisher projection within this video, as well as priority order, how you can arrange and visualize a certain molecule, is that if you know your priority order, okay, and let's say this is priority order 1, this is priority order 2, this is 3, this is 4. And we said 4 being away from us, and we, visualize basically from the top, keeping 4 away from us. So this is going to be your R configuration. And if you look at your mirror image, that's going to be 1. This is going to be 2, that's going to be 3. So in going from 1 to 2 to 3, that looks like it's going to be S. Another way you can visualize and still get the same result is if you visualize from here. So keep the even number away from you. So if you visualize from here, you will see that 1 will be on the left hand side, 3 will be on top, and 4 will be here. So in going from 1 to 3 to 4, it's going to still be R. And in going from 1 to 2 to 3, it's going to be still, so visualizing from here, it's the other way. This is what we already did. In going from 1 to 3 to 4, it would still be 1 to 3 to 4 because we are keeping 2 away from us. It will still be S. So as long as you keep 2 or 4, as long as you keep those away from you, you end up with the same configuration. On the other hand, if you try to keep the third priority or the first priority, then you get the opposite configuration, which is why I recall in the previous example my OH was on the dash line, and so I had to invert the configuration to get the correct configuration, if that makes sense. Okay, let's quickly learn how to convert the wedge and the dash to Fisher projection formulas. Fisher projection formulas. Essentially, Fisher projection formulas are a really nice way, easy way to have access to the R and S like really quickly. A lot of times you will see when you have like lots of chiral centers and the molecule is kind of complicated, it's difficult to visualize the R and S very quickly. It's simple, it's rather easy to do it if you have just one carbon atom, but if you have like 10 and you have 10 stereogenic centers and you have to look at the R and the S for each of those, it can be quite cumbersome. And so in that case, you should know how to convert, first off, how to convert your wedge and the dash into your Fisher format. So let's say this is your tetrahedral. You would have to view from the side. Okay, and as you're viewing that, you would see that essentially the A would be on the left hand side, B would be on the right hand side. The X and Y are going to point backwards to maintain the tetrahedral. And that's your Fisher formula. So in case of Fisher formula, what you do is you again assign the same stereochemistry and or the priority order rather, and then you look at the molecule and look at the least priority group, whether it's on the horizontal line or whether it's on the vertical line. As long as your least priority group is on the vertical line, you're fine. But if it's on the horizontal line, then you will need to invert the configuration. Let's take a look at one or two formulas to see if we are able to apply this or not. If somebody asks you how many stereogenic centers are present over here, hopefully you can see that there are two. So here you have one, here you have two, the second one. So when you give the priority order, oxygen of course is going to go with the highest priority, hydrogen is going to get the least priority. In this case you have a carbon connected to a nitrogen, and the top case you have carbons going to other carbon atoms, so that's the one that will go, that will get the, this is the one that will get the second priority, this is the one that will get the third priority. And if you're going, let me erase the 1 and 2 from here to avoid any confusion. And so if you're going from 1 to 2 to 3, it looks like you're going anti-clockwise, but then hydrogen is on the horizontal line, so you would say that this is actually R. Okay, so all you got to do again is get the priority order straightened and see whether it's clockwise or anti-clockwise, and then ask yourself one thing: the least priority group, is that on the horizontal line or is that on a vertical line? If it is on a horizontal line, call it R, so invert the configuration. If it's on vertical line, you're good. Let's try to put that in perspective with respect to the second carbon as well. So here the highest priority will be on nitrogen, least on hydrogen. Of course the top bond is going to be 2 and the bottom bond is going to be 3 on the methyl. So it looks like we are going the R way, but then again we'll have to invert this configuration to S because hydrogen is on the horizontal line. Now if you try to get the mirror image of that, your OH, the H would be here, OH would be here, the big benzene ring is going to be here, NHCH3 and CH3 over here. So hopefully you can see that my configuration should come out to be S and R. And let's, for the sake of argument, just, assign the priority order and go through it very quickly. You are going in an R manner, clockwise manner, but since hydrogen is on the horizontal line, it will have to be converted to S. And same way, if you have nitrogen, which is 1, this is 4, this is 2, this is 3, and going from 1 to 2 to 3, you were going S, but since again hydrogen is on horizontal, you will have to invert it to R. So we did end up with the configuration that we expected from our from the fact that these were enantiomers. But this is not the only way that this molecule can exist. You can have a format in which half of the molecule is going to have the same configuration. So let's say since we have two chiral centers, I'm going to keep half of the configuration the same, and I'm going to rotate half of the molecule. So let's just switch the NH and CH3 and the CH3 over here. So hopefully you can see over here that the configuration of the first carbon is going to come out to be R, much the same way as we did previously. And the configuration of the bottom part, since it kind of matches the mirror image, that will come out to be R as well. So notice the configuration now. You had RS, and the new molecule that I just wrote is an RR. Situations such as these, where half of the configuration is exactly same as the as your starting enantiomer, and the other half is inverted, these molecules are said to be in a relationship that they are diastereomeric. Diastereomeric. So I introduced the term enantiomeric earlier. These are diastereomers. Enantiomers would mean they have completely inverted configuration. That means if you had an RS system, it's going to give you an SR system. On the other hand, if you're thinking about a diastereomer, half of it is going to be exactly the same. The other half would be inverted. So in this case, your possibilities are the RR and the SS. They themselves are enantiomeric in nature, but they are diastereomeric with respect to both of these cases. So if somebody asks you, what is the relationship between A and B and C and D, you would say A and B are enantiomers of each other. C and D are enantiomers of each other. On the other hand, A and C are diastereomers of each other. B and C are also diastereomeric. B and D are diastereomeric. A and D are diastereomeric as well. So in case of a diastereomer, you keep the configuration constant for one of the carbons, you invert it for the other one. In case of an enantiomer, you completely invert the configuration. All right.